Hello everyone and welcome to the beginning of the end of this course. And in this hour, we are going to start the topic of semiconductor. On an average, 3 questions are coming from this particular topic every year in your NEET examination. 1 from PN junction, 1 from transistors and 1 from logic gates. So try to master this particular topic properly. You must read NCERT for this chapter exclusively. And as well as I suggest all students to solve as many questions as they can get their hands on based on the topic of semiconductor. This chapter is theoretical, so listen out every line which I say here very carefully. The question can be framed on any single line, so you need to revise this hour again. So without wasting time, let's start the hour of semiconductor. So the first thing we are going to talk in this hour is something called energy bands. I know that you have heard of a term Pauli's exclusion principle in chemistry. When the teacher teaches Pauli's exclusion principle, they say that no 2 electrons in an atom can have all the 4 quantum numbers same. In the world of physics, we talk in terms of energy. So we say that Pauli's exclusion principle means that no 2 electrons can have the same energy. Now to understand that, Pauli's exclusion principle works even for all the electrons present inside a crystal. The chapter we are learning is semiconductors. So I am going to talk about the general semiconductors. And the generally used, most used semiconductor material is silicon and germanium. Now, if we talk about silicon, silicon belongs to the carbon family. And in carbon family, every single atom has got 4 valence electron. So if you think of a crystal of silicon, each silicon atom will have 4 valence electron. To satisfy its octet, it will form 4 bond with 4 another silicon atom in the neighboring. So if you think of a silicon crystal, it will look something like this. Every silicon atom will form bond with 4 another silicon atom in the vicinity. Now to understand that I am drawing in 2D, but it is not a planar structure. It's a 3-dimensional structure. Think of the structure of diamond, kind of that. Now here I am telling you that each silicon atom has got 4 valence electron, and the Pauli's exclusion principle works even for a crystal. So no 2 electron in this whole crystal containing many silicon atoms can have the same energy. So if we start thinking of the energy level of the electrons present in the valence shell of every silicon atom, you do not get a discrete energy level. So for every silicon atom, if you look what is the energy associated with its valence electron, you will find that there are many different energies, and these energies, when taken for all the electrons together, they form a band. This band is called valence band. So one more time, what is valence band? Valence band is the range of all the energy associated with the valence electron of the silicon atom. Now sometime due to some thermal agitation or something, some of the electrons which are bonded here get sufficient energy and they break the bond and move out. Once these electron gets sufficient energy to break the bond and move into the crystal, they start conducting electricity. They become free electrons. The energy associated with all the free electrons present in the crystal, if plotted on the energy graph, you again find that there are many different energy associated with all the conduction electrons. And the range of all these energy forms a band, and that is called conduction band. No doubt that the electron in the conduction band will have more energy than the electron in the valence band, because it takes some energy in the form of photon or thermal agitation for the electron to break the bond and to become a free electron. That's why the energy of conduction band is greater than the energy of valence band. So let's start learning them one by one. So first of all, what is valence band? So energy band formed by series of energy level of the valence electrons is called valence band. Next thing, what is conduction band? The energy band formed by series of energy levels containing conduction electrons. So if you draw the energy levels of different conduction electrons on an energy level diagram, you will find that there are many electrons which have sufficient energy to be free to move anywhere in the crystal. And if you draw their energy level on a diagram, all these energies form a band, and that is called conduction band. No doubt, energy of the conduction band is greater than energy of the valence band. And the energy gap between the conduction band and the valence band is called forbidden energy gap. So, what is the meaning of forbidden energy gap? Energy gap between the conduction band and the valence band is called forbidden energy gap. Do notice here, somebody might have just called it energy gap. Why do they call it forbidden energy gap? Because in this crystal you won't find any electron having energy level between the energy level of the valence electron and those of conduction electron. Hence forbidden energy gap. None of the electron has got energy anywhere between the energy level of valence band and the conduction band. Now let's understand that no free electron is present in forbidden energy gap. And bachcho, width of forbidden energy gap depends upon the nature of the substance. For example, if it is very difficult for the electrons to move from valence band to the conduction band, then the energy gap is large. If it is very easy for the electrons to move from valence band to the conduction band, then the energy gap is less. On the basis of which type of material we are talking about, we can determine what has to be the energy gap. So let's understand it more. For the case of conductors, there is no energy gap. That's why in case of conductors, electrons can easily move from valence band into conduction band. And that's why a conductor has got so many number of free electrons, the electrons which are free to move anywhere within the crystal. When we talk about insulators, then we know that insulators are the substances in which we do not get free electron. It means that the number of electrons in the conduction band are negligible. And the number of electrons in the conduction band are negligible because they do not get sufficient energy to move from valence band to conduction band. So do understand, in case of insulator, the energy gap, the forbidden energy gap between the valence band and the conduction band is large. When we talk about semiconductors, the chapter we are discussing right now, in case of semiconductor also, there is some energy gap between the energy level of valence band and the energy level of conduction band. But do understand, this energy gap is small. So some of the electrons present in the valence band can get sufficient energy to move from valence band into conduction band. But not many of them, only some of them. If they ask you the energy gap is highest in the case of what? You will say energy gap is highest in the case of insulators, then in the case of semiconductors, and practically there is no energy gap in the case of conductors. Now bachcho, we need to understand that as temperature increases, the forbidden energy gap decreases very slightly. So on heating a substance, it becomes more and more easy for the electrons present in the valence band to move to the conduction band. And on heating, due to thermal agitation, the energy gap between the valence band and conduction band decreases. So now we are going to talk about holes in semiconductors. I know that you are familiar with the terminology that there are two types of charge carriers in semiconductors. There are electrons and there are holes. But what exactly are holes? Let's understand it here. So understand that at absolute zero temperature, absolute zero means not 0 degree centigrade, at 0 Kelvin, conduction band of a semiconductor is completely empty because none of the electron present in the valence band gets sufficient energy to move to the conduction band. That's why conduction band is completely empty. There are no conduction electron, and hence the semiconductor behaves as an insulator. So what you need to remember from here, at absolute 0 Kelvin, a semiconductor behaves as an insulator. But we know that things in real world are not at 0 Kelvin. They are at way higher temperature. So when the temperature increases above 0 Kelvin, the valence electron acquire thermal energy. And due to this thermal energy, few of the valence electrons get sufficient energy to move from valence band into the conduction band. So valence electron acquire thermal energy to jump to the conduction band due to the breaking of the covalent bond. If they jump to conduction band, they leave behind the deficiency of electron in the valence band. This deficiency of electron is known as a hole. And do understand that a hole is considered as a seat of positive charge, having magnitude of charge equal to that of an electron. Sir, I'm not getting this thing. Can you elaborate? Let's see. For the sake of understanding, I am again taking the silicon crystal. And in silicon crystal, we know that each silicon atom forms covalent bond with 4 another silicon atoms present in the vicinity. Now let's say, due to thermal agitation, few of the valence electrons get sufficient energy to move from valence band to the conduction band. So if let's say this particular electron gets sufficient energy, it will move from valence band into the conduction band. So you will get one free conduction electron which is now free to move anywhere in the lattice. Now since this electron has jumped out, this bond will be broken and this space is empty. This empty space is called the hole, the vacancy. Do understand that once this bond is broken, the electron present on this another silicon atom will be still here. Now what happens when we apply an electric field? So again, think of the silicon crystal. Think of the bond we have broken. And once this bond has been broken, this electron has moved into the conduction band. So here you get a hole and here you have got an electron. Now we are talking about semiconductors, current flow here. And to make the current flow, you have to apply electric field. Let's say someone places this particular silicon crystal in an external electric field and the external electric field is towards right. In which direction will the electrons present in this silicon crystal will experience a force? So sir, electrons are negatively charged particles. If you deploy an electric field towards right, the electrons will experience a force towards left. My other question, which electrons will experience a force towards left? Conduction electron, valence electron, all the electrons. So all the electrons have charges. So each and every single electron present in this crystal will experience a force in direction opposite to electric field. Now this guy, this electron is free. So it will move in direction opposite to applied electric field. And you will say that when this electron moves in direction opposite to electric field, we get a current due to the motion of electron in the direction of electric field. Current is predominantly defined as the flow of positive charge. If the positive charge goes towards right, you say that current is towards right. If the negative charge goes towards right, you say that current is towards left. And here, the free electron will move in direction opposite to the applied electric field. So you will say that due to the motion of this electron, we are getting current in the direction of applied electric field. There is one more type of current, the current due to the motion of the hole. Do understand, each and every single electron in this crystal experiences a force in direction opposite to field. So this electron can find a place where it can jump due to the force. This electron can jump and occupy the hole here. Because of which, here you will find an electron and here you will observe a hole. If I asked you, in which direction did the hole move? You will say that the hole moved in direction of electric field. Somebody else might say, sir, hole didn't move. The electron moved in direction opposite to electric field and occupied the position of the hole, and that's why you get a new hole. Yes, but if we talk as if hole is also a particle, in which direction did the hole move? Sir, the hole moved in the direction of electric field. So hole acted like a positive charge. Now do understand, again, even due to the motion of hole, which is nothing but electrons jumping and creating holes ahead, due to the motion of holes also we get one more type of current, and that current is called current due to hole. Irrespective of the nature of the charge on the charge carrier, we find that current due to both electron and hole is in the same direction as that of the applied electric field, and this is something we learned even when I was teaching you current electricity. So understand that a hole is considered as a seat of positive charge, considered, not actually, having magnitude of charge equal to that of an electron. Magnitude of charge, we treat that hole has got positive charge. Do understand that holes acts as virtual charges, although there is no physical charge on it. So hole act as a virtual charge. There is no real charge on a hole. Hole is nothing but a vacancy, but other electrons jump to occupy that vacancy, moving in the direction opposite to electric field. Hence we say hole move in the direction of electric field. So the next point, mobility of hole is less than that of electron. When you deploy the electric field, electrons find it easier to move. Why? Because they are free in the conduction band. But the process of motion of hole is complex. Since the process of motion of hole is complex, we say that the mobility of hole is less than that of electron. So keep it in mind, the mobility of hole is less than that of electron. Some people like to say it this way as well. Effective mass of hole is more than that of electron. Because holes have got lower mobility, it is difficult for holes to travel. We say that the effective mass of hole is more than that of electron. Many a times I have found students arguing that this is a rubbish statement, sir. Hole is a vacancy, hole is emptiness, hole is nothing. How can it have more mass than the electron? It comes from the idea of mobility. Since the process of motion of hole is complicated, holes are less mobile compared to electron, and since they are difficult to move, that's why we say that their effective mass is more. Next bachcho, let's talk about type of semiconductors, and the first type we are going to talk about is called intrinsic semiconductors. Intrinsic semiconductors are also called pure semiconductors when nothing is mixed with the semiconductors. So if you have only a crystal of silicon atoms, there are only silicon atoms and no other type of atoms present, you say that this is a crystal which can qualify as a intrinsic semiconductor. So bachcho, a pure semiconductor is called intrinsic semiconductor. It has thermally generated current carriers. We have learned that in case of semiconductors at 0 Kelvin, no electron will move from valence band to conduction band. So there will be no conduction electrons, there will be no holes, there will be no charge carriers. At room temperature, we find that there are some charge carriers present in the semiconductors, and those charge carriers are thermally generated charge carriers or current carriers. Silicon and germanium have 4 electrons in the outermost orbit of the atoms. The atoms are held together by covalent bond, and every time due to thermal agitation, one of the electron gets sufficient energy to move from the valence band to the conduction band. This covalent bond gets broken. Next bachcho, free electrons and holes both are charge carriers, and number of electrons in the conduction band equals to number of holes in the valence band. So if you have got an intrinsic semiconductor and assume that this pure semiconductor was initially at 0 Kelvin, so there was no free electrons. Now as you started to increase its temperature, as you started heating it up, you will find that some of the electrons get sufficient energy to move from valence band to the conduction band. Every time one electron moves from valence band to conduction band, one covalent bond gets broken and one hole is created. So do understand that the number of free electrons per unit volume in a pure semiconductor, in an intrinsic semiconductor, is exactly equal to the number of holes per unit volume. Next बच्चों, the drift velocity of electron is greater than that of hole. We know that the drift velocity is nothing but mobility times the applied electric field. Since the mobility for the hole is lower, we say that the drift velocity for the hole is lower because its motion of transfer is complex. So remember that electron has got higher mobility, electron has got higher drift velocity. Next point, bachcho. In intrinsic semiconductor, in a pure semiconductor, the number of free electrons per unit volume equals to number of holes per unit volume is equals to Ni. What is Ni? Ni means number of intrinsic sites per unit volume. For example, in the entire crystal, when you heat it up, at let's say temperature of 20 degrees centigrade, you find that there are 20 sites, 20 places in this crystal at which the electron has moved from the valence band to the conduction band. So if there are 20 sites at which the electron has moved from valence band to the conduction band, how many number of free electrons you will have? Sir, 20. How many number of holes you will get? Sir, 20. How many number of intrinsic sites you have, at how many places the electron got sufficient energy to move from valence band to the conduction band? Sir, 20. That's why the number of free electrons per unit volume is equal to the number of holes per unit volume is equal to the number of intrinsic sites per unit volume. Do understand that the number of intrinsic site means the places where the electron has got sufficient energy to move from valence band to the conduction band. Now, if you keep on providing heat, and let's say the temperature of this crystal increases from 20 degrees centigrade and becomes 30 degrees centigrade. Take a wild guess, the number of intrinsic sites will increase or decrease. So as you keep on heating the semiconductor, more and more number of electrons will be able to get sufficient energy to move from the valence band to the conduction band. So let's say on increasing the temperature, the number of intrinsic sites for this crystal become 53. It means that there are 53 places in this crystal from where the electron has moved from valence band into the conduction band. So the number of free electrons will be 53. The number of holes produced will be 53 when the number of intrinsic sites are 53. Next, bachcho. Because of less number of charge carriers at room temperature, intrinsic semiconductors have low conductivity. So why they have low conductivity? Because very few number of electrons get sufficient energy to move from valence band to the conduction band. Think of it like 1 in 10 raised to the power of 8 to 10 raised to the power of 10 electrons get sufficient energy to move from valence band to the conduction band. So because of less number of charge carriers at room temperature, intrinsic semiconductors have low conductivity, so they have no practical use. So sir, which type of semiconductors have got practical use? Extrinsic semiconductors, also called doped semiconductors. We will talk about them in a little while, but before, let's see this. Net current and conductivity. First of all, I have just told you guys, if you have got a crystal of, let's say, pure silicon, intrinsic semiconductor, then when you deploy some electric field, we know that due to the motion of electron in the direction opposite to electric field, you get a current due to the motion of electron in the direction of electric field. And due to the motion of hole in direction of electric field, you get a current due to hole in direction of electric field. If somebody asks you what is the net current, you will say that net current is current due to electron plus current due to hole. And we have learned that for a pure semiconductor, the number of free electrons per unit volume is same as the number of holes per unit volume. So can you tell me, out of these two currents, which one will be greater, or both of them is going to be equal? Many a time students answer this question that in a pure semiconductor, since the number of free electrons per unit volume is same as the number of holes per unit volume, that's why the current associated with both of them has to be equal, and that is not at all correct. We need to think a little bit more. We know that current, in the topic of current electricity, we learned that current equals to NEAVD. No doubt, for this crystal, the number of free electrons is same as the number of holes per unit volume. The charge on both of them is same. The cross-sectional area of the crystal available is same, but better the drift velocity for electron is greater than the drift velocity for hole, because hole moves through a complex pathway. That's why we say that the current due to electron is more than the current due to hole. So the net current is nothing but current due to the flow of electron plus current due to the flow of hole, but the current due to the flow of electron is higher than the current due to the flow of hole, as electron has got higher mobility. Now let's talk about conductivity. We know that J equals to sigma E. We have learned this in current electricity. Sir, what is J? Beta, J is called current density. Current density. What is sigma? Sigma is conductivity. And what is E? E is the electric field. So J equals to sigma E. We also know that I equals to NEAVD. Here, if I bring the cross-sectional area to the left-hand side, I get I by A. And I by A becomes nothing but current density. So current density can be written as NEVD. And we know that we can write the drift velocity as mobility times the electric field. Now what I want you to do is compare these two equations. J equals to sigma E, J equals to NE mu E. So from here you can say that the conductivity is nothing but the number of free electrons per unit volume multiplied by E multiplied by mu. When we are talking about general charge carriers, we say that the conductivity is nothing but the number of charge carriers per unit volume multiplied by the charge on the charge carrier multiplied by the mobility of the charge carriers. But do understand, in the case of an intrinsic semiconductor, in the case of a pure semiconductor, both electron and hole contribute to the flow of charge. So we say that for a pure semiconductor, the conductivity is equals to the number of free electrons per unit volume multiplied by charge on electron multiplied by mobility of electron. Plus, there is also current being conducted due to the motion of hole, and its contribution to the conductivity will be number of holes per unit volume multiplied by effective charge on the hole, which is same as the charge on the electron multiplied by mobility of the hole. So we say that the conductivity of a pure semiconductor is nothing but Ne E mu E plus Nh E mu H. You can take E common. And I recommend all of you to remember this particular result. We talked about this in the topic of current electricity. So bachcho, when some potential difference is applied across a piece of intrinsic semiconductor, pure semiconductor, current flows in it due to both electron as well as hole. So if you visualize the case, if you apply a potential drop across a crystal made up of pure semiconductor, the electron move in direction opposite to applied field, the hole move in direction of applied field, and because of motion of both of them, you get the current in same direction. So you say that the net current is nothing but current due to electron plus current due to hole, in which current due to electron is higher than the current due to hole because electrons have got higher mobility. Now if we talk about conductivity, so hence conductivity for a semiconductor is nothing but conductivity due to the moving electrons plus conductivity due to the holes. So you say that the conductivity comes out to be nothing but NE mu E plus NHE mu H, and you can take the E common, so the conductivity comes out to be this, and this is important. Later we are going to talk about some special type of semiconductors. Those will be extrinsic semiconductors. There will be P type, there will be N type. In P type we will say that the number of hole is greater than the number of electron. In N type we will say that the number of electron is greater than the number of hole. So when I write conductivity for P type, I neglect out this electron term, and when I write conductivity for the N type, I neglect out this hole term. That will be used later, so do remember this, it gets asked many a times. Now bachcho, we can say that here mu E represents the drift velocity of electron divided by the applied electric field. We have learned that drift velocity is nothing but mobility times electric field. So mobility of electron is nothing but drift velocity of electron upon the applied electric field, and that is called the mobility of electron. And beta mu H represents the drift velocity of hole divided by the applied electric field, and that is nothing but mobility of the holes. So now we are going to talk about the other type of semiconductors, the useful one, and those are called extrinsic semiconductors. What are extrinsic semiconductors? You take an intrinsic semiconductor, pure semiconductor, add up some impurity to it, and what you get is extrinsic semiconductor. Now here the terminology impurity is highly misleading. It is not impurity. Scientists are not idiots. They won't add dirt to something to make it better. The proper terminology that we should use rather than impurity is dopant. You might have heard of the athletes undergoing a dope test, because athletes add up something to them, they consume something to enhance their performance. Dopant are something added to the pure semiconductor so as to enhance their performance, and hence what you get is extrinsic semiconductors. So extrinsic semiconductors are also called impure semiconductors, but I personally like to call them enhanced semiconductors. The process of adding impurity is called doping, so as to enhance the performance. We need to understand that we add impurities which are of two types. Either we add up pentavalent impurity or we add up trivalent impurity. When I say pentavalent impurity, it means that we add up to the intrinsic semiconductor which has got valency of 4. Here we are talking about pure semiconductors of silicon and germanium. They belong to the carbon family. So either we add up impurities or dopant which belong to the nitrogen family. Each member of the nitrogen family has got 5 valence electrons, hence pentavalent. Or we add up impurity of the boron family. In boron family, every atom has got 3 valence electron, hence trivalent impurity. So when we add up pentavalent impurity, the element whose atom has got 5 valence electrons. Example As, P, Sb. These are called donor impurities. Why they are called donor impurities? Think of the phosphorus atom. It has got valency of 5. If you add up a phosphorus atom into a silicon crystal, let's say here phosphorus, using the 5 electrons, with 4 of them, it will form 4 bonds with the nearby silicon atoms, and 1 electron will be free. And this 5th electron can be easily excited into the conduction band. Hence, we say it's a donor impurity. It donates the electron. To the contrary, when we add trivalent impurity, the element whose each atom has got 3 valence electrons are called trivalent impurity. Example indium, gallium, aluminium, boron. These impurities are also called acceptor impurities. Why? Because they have got 3 valence electrons. So if you, let's say, add up boron, it has got only 3 electrons. So 3 of the electron will form 3 bonds with the surrounding silicon atom and you will get one ready-made hole. So that's why they are called acceptor impurities. They can accept electron from the surrounding silicon atom. Now bachon, moving on and talking about them one by one. So first talking about N-type semiconductors. So if you take intrinsic semiconductor, pure semiconductor, and you add a pentavalent impurity to it, a type of impurity which has got valency of 5, so it must belong to the nitrogen family. What you get is N-type semiconductor. We call it N-type semiconductor because in this type of extrinsic semiconductor we get excess electrons. For each pentavalent impurity added, we get one free electron. This electron is not bounded to any of the surrounding atoms and hence it can be excited easily. Now bachon, do understand that in case of N-type semiconductors, since you have added pentavalent impurities, you are getting more number of free electrons. So the majority charge carriers in an N-type semiconductor is electrons. You get more number of electrons. But do understand, still you have got intrinsic sites. So still there are places within the crystal where the electron has moved from the valence band into the conduction band. So still you will have holes. But it's just that since you have added pentavalent impurity, you will have more number of free electrons compared to holes in the crystal. So we say that in an N-type semiconductor, the majority charge carriers are electrons and the minority charge carriers are holes. These holes are still there due to the intrinsic sites. Now do understand that we add up these impurities as part per million. So one atom to every 10 raised to the power of 6 atom of the crystal. So if you add one phosphorus atom for every 10 raised to the power of 6 atom of germanium, you will get one excess electron for every 10 raised to the power of 6 atom of germanium. And the concentration of intrinsic site was that in one atom out of 10 raised to the power of 8 to 10 raised to the power of 10 atoms you used to get intrinsic sites. So because of addition of this pentavalent impurity, now the number of electrons have shot up, but still there are holes. So the holes are minority charge carriers while electrons are majority charge carriers. So the number of free electrons per unit volume is way greater than the number of holes per unit volume. And hence, when you place this type of crystal in an external electric field, the current due to the electrons become way higher than the current conducted due to the holes. No doubt, the current due to the motion of both electron as well as hole is in the direction of applied electric field. But since the number of free electron is way greater now than the number of holes, the current associated with the motion of electron is higher than the current associated with the motion of holes. Now bachon, we say that the conductivity for such a crystal is given by Ne mu E. We learned that for a pure semiconductor, the conductivity was given by Ne mu E plus Nhe mu H. In case of N-type semiconductors, since the number of free electrons per unit volume is way higher than the number of holes per unit volume, we can neglect out this term and say conductivity is nothing but Ne mu E. What is Ne? The number of free electrons per unit volume. What is mu E? The mobility of the electron. And what is E? The charge on the electron. You just substitute the magnitude here. Now bachcho, understand that N-type semiconductor is electrically neutral. People start thinking that N-type semiconductor should be negative. P-type semiconductor has to be positive. What did you do to create an N-type semiconductor? You took an intrinsic semiconductor, a pure semiconductor, and then you just added up a pentavalent impurity. I ask you, Are you adding phosphorus plus or phosphorus minus? Sir, we are just adding phosphorus. So beta, if to a neutral crystal, if you have added a neutral atom, then the overall crystal has to be neutral. This electron belonged to phosphorus. Once this electron comes out, this phosphorus atom gets a net positive charge. There is no hole, but it gets a net positive charge. So this electron and this positive charge balance out each other. So do understand that N-type semiconductor is electrically neutral, not negatively charged. That is a common misconception. Now, next thing you need to know is impurity is called donor impurity. Why? Because there is one electron which doesn't form any covalent bond. So that is free and easy to be excited. And since it is easy to be excited, the impurity donates the electron, hence called donor impurity. Next बच्चों, donor energy level lies just below the conduction band. What is the meaning of it? If you think of the conduction band and valence band for the intrinsic semiconductor, for the pure semiconductor, the electrons which are going to be excited into the conduction band already have got energy close to the conduction band. That fifth electron of the phosphorus which wasn't bonded has got energy closer to the energy of the conduction electron. Hence, it can be easily excited. So do remember, in case of N-type semiconductor, the donor energy level lies closer to the conduction band. Now we will talk about other type of extrinsic semiconductor, and that is P-type semiconductor. So how do you get a P-type semiconductor? You take an intrinsic semiconductor, a pure semiconductor. Here we have taken crystal of germanium, and to it you add up a trivalent impurity, an impurity whose valence electron are 3. And what you end up getting is called P-type semiconductor. Now do understand that if you add up, let's say, boron to the crystal of germanium, 3 of the boron electron will form bond and you will get 1 vacancy. So you got 1 ready-made hole for every single boron atom added. Again repeating, the number of intrinsic sites are 1 in 10 raised to the power of 8 atoms to 1 in 10 raised to the power of 10 atoms. But we add up boron in part per million. So we add up 1 boron atom for every 10 raised to the power of 6 germanium atom. And because of this, we get 1 ready-made hole for every 10 raised to the power of 6 germanium atom. Hence, the number of holes becomes way greater than the number of free electrons in case of P-type semiconductor. So for a P-type semiconductor, the majority charge carriers are holes. You get P-type semiconductor when you add up trivalent impurity. And definitely the minority charge carriers have to be electrons. So the number of holes per unit volume are way greater than the number of electrons per unit volume. And hence we say that the majority charge carriers are holes and the minority charge carriers are electrons. So that can be written as the number of holes per unit volume is way greater than the number of electrons per unit volume for a P-type semiconductor. And hence, if you place this crystal in an external electric field, you get current due to both electron as well as hole. But since the number of holes are way higher than the number of electrons in case of P-type semiconductor, the current flowing due to the hole is way greater than the current flowing due to the flow of electrons. Now, bachcho, same type of things. The conductivity for a P-type semiconductor is written as the number of holes per unit volume multiplied by the mobility of hole multiplied by charge on the hole. There is technically no charge on hole, but we take the charge on the hole to have the same magnitude as the charge on electron, which is 1.6 into 10 raised to the power of minus 19 coulomb. Now, P-type semiconductors are also electrically neutral, just like N-type semiconductor. They are electrically neutral. You take a neutral germanium crystal, you add up neutral boron atom, the crystal is neutral, not positively charged. So just because people see P-type, N-type, they think that, okay, P-type means positively charged, N-type means negatively charged. No. Both of them are electrically neutral. Next beta, impurity is also called acceptor impurity because it has got a ready-made hole. It can accept electron of another germanium atom. That's why I called acceptor impurity. And if we talk about energy level, acceptor energy level lies just above the valence band. So valence electron of other germanium atom can easily occupy this space. So acceptor energy level lies closer to the valence band. In case of N-type semiconductor, the donor energy level lies closer to the conduction band. This is something that you have to remember. Now bachon, moving on and talking about the important thing, that is law of mass action. For pure semiconductors, we learned that the number of free electrons per unit volume equals to number of holes per unit volume equals to number of intrinsic sites, right? For extrinsic semiconductors, we say that the number of free electrons per unit volume into number of holes per unit volume equals to number of intrinsic sites whole square. So bachcho, remember that for extrinsic semiconductors, for impure semiconductors, for doped semiconductors, we say that the number of free electrons per unit volume into number of holes per unit volume equals to number of intrinsic sites whole square. You can think over it this way. If you took a pure crystal, for a pure crystal, the number of free electrons equals to number of holes equals to number of intrinsic sites. Now let's say I add up to this pure crystal trivalent impurity. If I add up trivalent impurity, which type of semiconductor I will get? P-type. And now the number of holes will increase. As the number of holes increases, let's say become double, the number of electrons becomes half. So when the number of holes becomes double, the number of free electrons per unit volume becomes half, so that their multiplication remains constant equals to number of intrinsic site whole square. We get this relationship from chemical equilibrium. That's why you must have learned this term even in chemistry, law of mass action. Now bachcho, understand that for P-type semiconductor, when you have to use this equation, for P-type semiconductor, take the number of holes as the number of trivalent impurities added per unit volume. So if you need to solve a question in which they tell you number of intrinsic sites and how many number of trivalent impurity has been added per unit volume, then better treat the number of holes simply as the number of trivalent impurity added per unit volume. You will get the number of free electrons per unit volume. And for an N-type semiconductor, take the number of free electrons per unit volume as the number of pentavalent impurity added. So keep these two statements in mind, and I promise you, you will be able to solve any question which comes based on law of mass action. If in the question they give you P-type semiconductor, then better take the number of holes per unit volume as number of trivalent impurity added per unit volume. And if they give you N-type semiconductor, then take the number of free electrons per unit volume as the number of pentavalent impurity added per unit volume. Simple. You will get the answer for sure. Moving on. The number of atoms of impurity element is about 1 in 10 raised to the power of 6 atom of the semiconductor. So we add impurity nearly in part per million, 1 for every million atom of the crystal. Next bachcho, the number of free electrons per unit volume is not same as the number of holes per unit volume. In case of N-type, the number of free electrons per unit volume is greater than the number of holes per unit volume. And for p-type, the number of holes per unit volume is greater than the number of free electrons per unit volume. Now bachcho, understand that their conductivity is high because you have doped them and they are practically used. So do understand, in case of intrinsic semiconductors, pure semiconductors, the number of charge carriers are so small that they are practically of no use. But once you have doped them, you have increased the number of charge carriers and now they are useful. So now moving on and talking about the important part of this hour from where the question will come in your NEET. So we will talk about something called PN junction diode. First of all, you need to understand what is the meaning of diode. Diode is something that lets the current flow in one direction but blocks the current when it flows in the other direction. So if I have drawn diode like this, it means that current is allowed to go from left to right, but current is not at all allowed to go from right to left. So a PN junction acts like a diode. You need to remember this simple idea. Now bachcho, when a semiconductor wafer, you take a silicon crystal, a silicon wafer, is doped with both trivalent and pentavalent impurity, we get PN junction or PN junction diode. So you take a silicon crystal, to one side of this silicon crystal, you add up, let's say, trivalent impurity. So this side of the silicon crystal where you have added trivalent impurity, that becomes p-type. And on the other side of the same wafer, you add up, let's say, pentavalent impurity. When you add up pentavalent impurity, this becomes n-types. Do understand that every time we get a PN junction, it doesn't mean that you took a p-type semiconductor, you took an n-type semiconductor and placed them in contact. This won't work because here we are talking at the atomic level. No matter how smooth a p-type semiconductor and an n-type semiconductor you take, when you place them in contact, still there is huge amount of gap between the conductors and hence the charge carriers can't move easily. That's why we have to create a PN junction on a single wafer. Now bachcho, you take a crystal, you add trivalent, pentavalent, you get a boundary that is called PN junction. Now to understand, both p-type and n-type semiconductors are electrically neutral. What is the net charge on a p-type semiconductor? 0. What is the net charge on an n-type semiconductor? 0. So when you add up the trivalent impurity and pentavalent impurity, before the charges move from here to there due to some reason, before they move, both the sides are electrically neutral. But you need to understand, on the crystal, one side you have added trivalent impurity. So this will be hole rich. It will have more number of holes compared to electron. So on the p side, the majority charge carriers are holes. And on the other side, where you have added pentavalent impurity, that's n side, there the majority charge carriers are electrons. So can I say that on the p side of the PN junction diode, we have got huge concentration of holes, and on the n side of the PN junction diode, we have got huge concentration of electrons. We know that things move from higher concentration region to lower concentration region, and this phenomena is called diffusion. So due to the difference in the concentration of the charge carriers on both the sides, they start to diffuse. The electrons on the n side start to move to the p side and start to occupy the holes there. Because of which, in a particular region near the junction boundary, on the n side you don't find electrons, on the p side you don't find holes, because the holes on the p side have been occupied by the electrons which came from the n side. So there is a region formed near the boundary in which you do not find any type of majority charge carriers, as if this region has been depleted of its majority charge carriers. And that's why the name of this region is called depletion region. the region that has been depleted of its majority charge carriers, depletion region. So bachcho, on the p side, holes are majority charge carriers, and on the n side, electrons are majority charge carriers. Due to difference in concentration of charge carriers, diffusion takes place. Electrons move from n side and occupy the holes on p side near the junction boundary. So this is called p-n junction boundary. Now we can say that hence the p side gets a net negative charge and the n side get a net positive charge. Sir, what do you mean? What do you mean? See here, bachcho. Initially, as soon as the p-n junction was created, both the p side as well as n side were electrically neutral. Yes. Now, electrons moved from the n side to the p side and occupied the holes at the place of p side. Yes, sir. Tell me, is there net charge transfer from one side to another? Yes, sir. Electrons move from n side to p side. Yes. So now p side will have a net negative charge. And since the electrons moved from n side to p side, the n side will have a net positive charge. So it will look something like this. Once the diffusion takes place, the electron has occupied the holes on the p side. You say that now the p side has a net negative charge and n side has a net positive charge. So an electric field now exists in the depletion region. Once more, what is the meaning of depletion region? Depletion region is the region that has been depleted of its majority charge carriers. On the n side, the majority charge carriers were electrons. But the electrons present on the n side near the junction boundary move from n side to p side due to diffusion, due to the difference in concentration, and occupied the holes there. Because of which the p side near the junction boundary gets a net negative charge and the n side near the junction boundary gets a net positive charge. And this region has been depleted of its majority charge carriers on both the sides, hence called depletion region. If I ask you, in the depletion region, an electric field exists from which side to which side, so you will say that, sir, once the diffusion has taken place, I know that now the n side has got positive charge and p side has got a net negative charge. So an electric field will exist in the depletion region from positive charge towards the negative charge. That is from n side to p side, and you need to memorize the entire script to answer any theoretical question that get asked from here. Now bachcho, talking about depletion region. Due to the loss of electrons and holes near the junction boundary, this region is depleted of its majority charge carriers. Hence, this region is called depletion region. Once more, due to the loss of electrons and holes near the junction boundary. Sir, why the loss of electrons and holes near the junction boundary? On the n side, electrons were majority charge carriers. On the p side, holes were majority charge carriers. Due to the difference in concentration of the charge carriers on both the sides, electron moves from n side to p side, occupying the hole there. So now the holes which were majority charge carriers on the p side are absent, and the electrons which were majority charge carriers on the n side near the junction boundary are absent. Hence this region is called depletion region. Next bachcho, the thickness of the depletion layer is of the order of 1 micron. When I say 1 micron, it means 10 raised to the power of -6 meter. So sir, for any p-n junction, you will get depletion region of thickness 1 micron. I'm saying of the order of, near about. Okay. So the thickness of depletion region is of the order of 1 micron. Next bachcho, width of depletion region decreases with the increase in doping level. Now this is something which is used many a time to explain Zener diode, and you should know this. So if you have got two types of p-n junction, one highly doped and one feebly doped. So think of the first case, feebly doped. So very less number of holes on the p side, very less number of electrons on the n side. And second case, highly doped, huge number of holes on the p side and huge number of electrons on the n side. Now question is, once the diffusion takes place, in which case the thickness of depletion region will be larger? When you have got highly doped p-n junction, the electron will have to travel very less distance on the p side to occupy a hole, and hence the thickness of the depletion region will be less. If you have got feebly doped p-n junction, then the electron will have to travel a greater distance on the p side before occupying a hole, and hence you will say that the depletion region will be thicker. So do understand bachcho that the width of depletion region decreases with the increase in doping level. The greater the doping level, the more will be the number of electrons and holes present. The greater the number of holes present on the p side, the lesser the distance the electron will have to travel before occupying the hole. So if the doping level is high, the depletion region is thin, and if the doping level is less, the depletion region is thick. You should know this. Next bachcho, on increasing the temperature, the thickness of the depletion region increases. Why sir? If you increase the temperature, it means that more and more number of electrons on the n side will get higher thermal energy. So more and more number of electrons will diffuse. So they will have to go deeper on the p side to occupy the hole, and hence the thickness of the depletion region will be higher. So if you take the same p-n junction and start to heat it up, you start to increase the temperature, then the thickness of the depletion region increases. Important point. Now bachcho, talking about something called potential barrier. We have already learned once the diffusion takes place, the p side gets net negative charge because the electrons have moved from n side to p side. Initially both the p side and n side were electrically neutral, and n side gets a positive charge. Because of this, an electric field exists from n side to p side, and we know that moving in the direction of field, potential decreases. So you can say that the potential of n side is higher than that of p side, because within the depletion region an electric field exists from n side to p side. Now since the potential of n side is higher than the p side, this potential difference created is called the barrier potential. Now why the term barrier will explain, but listen to it. So the potential difference created across the p-n junction due to the diffusion of electron and hole is called barrier potential or potential barrier. Now why do they use the term barrier? Think over it very carefully. We know that once the electrons have diffused to the p side gets negative charge, yes sir, n side gets positive charge, yes sir, and let's say here we get a potential difference of the p side and n side equals to 0.5 volt. Now this potential difference acts as a barrier. If any electron further wants to move from n side to p side, it should have a kinetic energy greater than 0.5 electron volt to move from n side to p side. Think over it. One electron started going from n side to p side more. As soon as the electron reaches the depletion region, this positive charge on the n side will attract it. The negative charge on the p side will repel it. This electron will be able to cross only if it has sufficient kinetic energy so as to overcome this potential barrier. So if the potential difference between the p side and n side is 0.5 volt, then this electron should have a kinetic energy greater than 0.5 electron volt to be able to cross. If this potential barrier is, let's say, 0.8 volt, then for any further diffusion of electron to take place from n side to p side, the kinetic energy has to be greater than 0.8 electron volt. So greater the potential barrier, more tougher it is for the electrons on the n side to move to the p side. Now bachcho, for germanium, this barrier potential comes out to be 0.3 volt. And for silicon based PN junction, this barrier potential comes out to be 0.7 volt. We need to understand that on an average, the barrier potential of PN junction can be taken as 0.5 volt. As for germanium, we get 0.3. For silicon, we get 0.7. So we have taken the average. Let's say on an average for all PN junctions, we get the barrier potential of 0.5 volt. And we know that the width of the depletion region is of the order of micron, 10 raised to the power of -6 meter. So we can say that the electric field in the region, the barrier electric field, will be equal to nothing but the potential drop divided by the distance in which the potential drop takes place. For uniform electric field moving in the direction of electric field, we can say that the electric field is nothing but potential drop upon the distance in which that potential drop took place. So we can say that E equals to potential drop upon the thickness in which that potential drop took place, and that will be equals to 0.5 upon 10 raised to the power of -6. 0.5 upon 10 raised to the power of -6 becomes 0.5 into 10 raised to the power of 6, and that gives you 5 into 10 raised to the power of 5 volt per meter. You need to understand this is huge strength of electric field that is present in the depletion region. Now, bachcho, if you have got this PN junction diode and here you have got depletion region, you can see that the potential of N side is higher than the potential of P side. If we think of the graph of potential versus the distance, as the electric field in the depletion region is from N side to P side, and we know that when we move in direction of field, potential decreases. When we move in direction opposite to field, potential increases. So if we move from left to right distance, then you will say in this region from here to here, no electric field, so the potential remains constant. In the depletion region, there is electric field from N side to P side. So as I go further up, the potential increases. And once I have crossed the depletion region, again, the field is 0, so the potential is constant. So constant, then increases, then constant. And this thickness is nothing but the thickness of the depletion region. So when we are moving on the P side till the time we have entered into the depletion region, the electric field strength is 0, so the potential is constant. Once we start moving in the depletion region, we know that in the depletion region, field is from N side to P side. When you move in direction opposite to electric field, the potential increases. And once you have crossed the depletion region and you are moving further distance, then you will say that again the potential will be constant, because in this region the electric field strength is 0. So this is the graph of potential versus distance as we move across a PN junction. Now, what we need to talk next is diffusion and drift current. And again, this is important. What is the meaning of diffusion current? What is the meaning of drift current? Because of concentration difference of holes and electron try to diffuse from their side to the other side. So holes try to diffuse from P side to N side, and electrons try to diffuse from N side to P side. I personally like to talk in terms of electrons because I understand the motion of electrons. It is difficult to talk in terms of motion of holes because holes are nothing, they are vacancies. So because of concentration difference, holes and electron try to diffuse from their side to the other side, quite obvious. Only those holes and electrons crosses the junction which have high kinetic energy, which have got kinetic energy greater than the barrier potential. This diffusion results in an electrical current from P side to N side, known as diffusion current. So how do you know that diffusion current is from P side to N side? Think over it. In a PN junction, on the P side, majority charge carriers are holes. On the N side, majority charge carriers are electrons. Why do they diffuse? Sir, because of the difference in concentration. Electron moves from which side to which side due to diffusion? Sir, electron moves from N side to P side. Beta, electron moves from N side to P side, as good as saying holes move from P side to N side. So if I ask you, due to diffusion, electron is going from N side to P side, what has to be the direction of diffusion current? Sir, current is predominantly defined in the direction of flow of positive charge. Electron is negative charge. So if the electron goes from n side to p side, you will say that diffusion current is from p side to n side, and you need to remember this. Diffusion current is from p side to n side. Now bachcho, let's talk about drift current. As electron hole pair, because of thermal collisions, are continuously created in the depletion region. Once the depletion region has been formed, it's not so that no more electron hole pair are created in the depletion region. It's a statistical model. Somehow, if some of the electron gets sufficient energy to move from valence band to the conduction band, again you will get an electron hole pair. Now visualize the PN junction. Think of the depletion region. Now you might have guessed by now that sir draws depletion region too thick, but I draw it too thick to make you understand. Think that it is of the order of micron, very thin. Now on the P side, we know that there is net negative charge. On the N side, we know that there is net positive charge. If due to statistics, one of the electron present within the depletion region gets sufficient energy to move from valence band to conduction band, you will get an electron hole pair. Now tell me in which direction this electron will move due to the electric field present in the depletion region. Sir, in the depletion region there exists an electric field from N side to P side. An electron is negatively charged particle. It will experience an electric force in the direction opposite to electric field. So since in the depletion region there exists a field from N to P, the electron will experience a force towards the N side. And the hole, which is treated as a positive charge, will experience a force in direction of field, that is towards the P side. Now if the negative charge goes towards N side, you will say that current is towards which side? So we will say that the current is from N to P, and due to the motion of hole, the positive from N to P, you will say that the current is from N to P. So do understand that in a PN junction we get two types of current. There is diffusion current and there is drift current. Diffusion current is due to diffusion, and that current comes out to be from P side to N side, while the drift current comes out to be from N side to P side. Let's understand drift current once more. As electron hole pair due to thermal collision are continuously created in the depletion region, there is a regular flow of electrons towards the N side and of holes towards the P side. So if there is a regular flow of electron and hole in the depletion region, this makes a current from N side to P side, and this current which is flowing in the depletion region due to the electric field present in the depletion region is called the drift current. So just remember, diffusion current P side to N side, drift current N side to P side. Simple. Now better understand that in steady state, once you have a PN junction and you have not connected it to any battery or anything, then under steady state, the diffusion current, which is from P side to N side, is equal to the drift current, which is from N side to P side, and hence the net current in the PN junction diode is 0. Now comes the important part, and that is biasing of PN junction. So when no external source is connected, diode is called unbiased. It is not at all biased. Okay, but when we connect external source, there can be two types of biasing. There can be forward biasing and there can be reverse biasing. Now let's talk about the type of biasing. So bachcho, we are going to talk about biasing, forward and reverse biasing. So we say means the way of connecting EMF source to the PN junction diode represents the type of biasing we have done. There are two types of biasing, forward biasing and reverse biasing. When do we say that a PN junction diode is under forward bias? So when P side is at higher potential compared to N side. Many a time teachers say a PN junction diode is said to be in forward bias when P connected to positive and N connected to negative. I say that a PN junction diode is said to be in forward biasing when P connected to higher and N connected to lower. For example, if you have this PN junction diode, if P is connected to 4 volt and N is connected to 6 volt, you will say that this is not forward biasing. For forward biasing, P side should be connected to higher potential and N side should be connected to lower potential. So if P side is connected to 10 volt, a higher potential compared to N side, then it will be said to be forward biasing. For forward biasing, you can even have potentials like P side connected to minus 2 volt and N side connected to minus 20 volt. It's just that the potential of the P side should be higher than the potential connected to the N side. That's the meaning of forward biasing. And then there is something called reverse biasing, the reverse thing. When N side is connected to higher potential compared to P side. So if you connect P side to higher potential, it is forward biasing. If you connect N side to higher potential, that is called reverse biasing. So if you have got PN junction, if you connect P to higher and to lower, it is said to be forward biasing. And again you have got PN junction, P connected to lower, N connected to higher. This is reverse biasing. Now beta, I want you to take a pause here and think with me really slowly. When you connect P to higher and to lower, you know that P side has been connected to higher potential, N side has been connected to lower potential. So you have applied an external electric field from P side to N side. Notice that the direction of this applied electric field is opposite to the direction of electric field in the depletion region, which is positive to negative. The electric field present in the depletion region does what? Sir, it creates a barrier potential. Forget this external electric field. Forget this battery. Due to this barrier potential, the electrons on the N side can't jump and reach the P side. If you want these electrons to now jump from the N side and to reach the P side and then to move the positive terminal of the battery so as to complete the current, the applied potential should be greater than barrier potential. So do remember that. Many a time I find students saying that when a PN junction is forward biased, current flows. No. When a PN junction is forward biased in such a way that the applied potential is greater than the barrier potential, then the electrons flow and then the current flows in the circuit. Do understand that this applied electric field applies force on majority charge carriers electron on the N side towards the depletion region, and it applies force on the holes on the P side, which are again majority charge carriers on the P side towards the depletion region. The force on positive charge is in direction of applied field. Hence, both the side, N side and P side, majority charge carriers on both the side are pushed towards the depletion region. Remember that when a PN junction diode is forward biased, the thickness of the depletion region decreases and the barrier potential also decreases. To the contrary, when your PN junction diode is reverse biased, it means that N connected to higher, P connected to lower. It means that we have applied an external electric field from N side to P side. And this time this external electric field is in the direction of the electric field in the depletion region. Now, both the electric fields oppose the motion of electron from N side to P side. Notice that what is the direction of force on this electron on the N side drawn as? So sir, if the external electric field is towards left, on this electron the force will be towards right. So the majority charge carriers on both the sides experience force away from the depletion region. And it becomes more and more difficult for the electron to move from N side to P side and then to the battery so as to complete the current. Hence, under the reverse biased condition, we say that we do not find any current due to majority charge carriers. Moreover, as the majority charge carriers on both the sides are moving away from the depletion region, the width of the depletion region increases, the barrier potential increases. So sir, what do we need to remember here? First, forward biasing, P connected to higher, N connected to lower. Reverse biasing, N connected to higher potential, P connected to lower potential. In forward biasing, the direction of applied electric field due to external source is opposite to the electric field in the depletion region. Even in forward biasing, so as to make the charge flow, so as to make this electron on the N side to be able to reach the P side, the applied potential should be high enough so that this electron can overcome the barrier potential. So for low applied potential, even in forward bias, no current flows. Second thing, in reverse bias, we keep N side at higher potential, P side at lower potential. This means that we are applying an external electric field which is in the same direction as the electric field in the depletion region. The electric field present in the depletion region creates the barrier potential, which makes it tough for electron to jump from N side to P side, and now you have placed an external electric field which further aids it. So now it is even difficult for electron to jump from N side to P side. Since the majority charge carriers on both the sides are moving away from the depletion region, in case of reverse bias, the thickness of the depletion region increases and hence the barrier potential increases, whilst in forward bias, both the sides, the majority charge carriers are pushed towards the depletion region thickness decreases and hence the barrier potential decreases. Talking ahead about the biasing. Now बच्चों, even in forward bias, no appreciable current flows till the time the applied potential is less than knee voltage. So if you think of the current versus potential graph, even in forward bias, for low applied forward voltages, you do not get any appreciable current, because for the electron to jump from N side to P side, the support from the external source should be such that the kinetic energy gained by the electron should be greater than the barrier potential. So for low applied voltages, you do not find current. But as once the applied voltage become big enough that the electrons on N side can now cross the barrier potential, the current starts to flow, and with the further increase in potential, the current starts to increase. So the current potential graph looks something like this. Do notice that in forward bias, given that the applied voltage is greater than the knee voltage, the diffusion current is large. Still there is some drift current in the PN junction, because still, no matter the type of biasing, electron hole pair are getting continuously created in the depletion region. So you say that diffusion current is from P to N, drift current is from N to P, and the net current comes out to be from P side to N side in forward biasing. Now for reverse biasing, in reverse bias, current flows through the diode only due to minority charge carriers. The current do not flow due to majority charge carriers, because on the N side as well as on the P side, on both the side, the majority charge carriers are pulled away from the depletion region. So they can't cross the depletion region. In case of reverse bias, the current flows due to minority charge carriers. If you visualize the forces on the electrons on the P side, where they are minority, and the forces on the holes on the N side, where they are minority, then you will find that the forces on them are towards the depletion region, and because of them current flow, but they are minority charge carriers, so the current flowing is not appreciable. So in reverse bias, current flows through the diode only due to minority charge carriers, hence no appreciable current till the junction breaks down. Now what is the meaning of junction breaks down? So if you think of the applied potential in the reverse sense versus the current, we have taken current from P to N to be positive. So in reverse bias, till the time the junction do not break, the field in this region is not so large that all the bonds starts breaking up, you do not find any appreciable current. But if you apply very large reverse voltage, then the PN junction breaks down, and once it breaks down, you get huge amount of reverse current. So under reverse bias, you say that diffusion current is from P to N, drift current is from N to P. There is a net small current flowing from N side to P side till the time it does not reach the breakdown voltage. So there is no appreciable current under the reverse biased condition till the time the PN junction do not undergo breakdown, and once it breaks down, then you start getting current even under reverse bias condition. So now we must understand the diode characteristic. Why do we say PN junction diode? So the current can flow from P side to N side under the forward biased condition, given that the applied potential drop is greater than knee voltage. And in reverse bias, no current will flow, though current will flow due to minority charge carrier, but we treat it as no current will flow. That's the diode characteristic of a PN junction. And the symbol used in a circuit to represent PN junction is this. Current can go from P to N, but the current can't go from N to P. Now bachcho, let's understand about breakdown. So there are two types of breakdown that we need to understand. One is called Zener breakdown and another one is called Avalanche breakdown. Let's understand them one by one. What is the meaning of Zener breakdown? When reverse bias is increased, yes, the electric field at the junction also increases, yes, because we know that under the reverse biased condition, the external applied field and the field in the depletion region are in the same direction. So when reverse bias is increased, the electric field at the junction also increases, yes. At some stage, the electric field becomes so high that it breaks the covalent bond creating electron hole pair. Sir, how can it break the covalent bond creating electron hole pair? I might have told you while teaching you electrostatic, if you take a plate of, let's say, positive charge and you take a plate of negative charge and you place between them a water molecule, H2O molecule. So on the oxygen, you have got partially negative charge. On the hydrogen, you have got partially positive charge. These hydrogen atoms, which have got partially positive charge, will be attracted towards the negative plate. And the partially negative charged oxygen will be attracted towards the positive plate. If you keep on increasing the strength of charges on these two plates, making the positive plate more and more positive and the negative plate more and more negative, then at a certain point, the force on this oxygen and hydrogen will be so large that it will break the bond. So, if you have got a PN junction diode and it is reverse biased, then the strength of electric field due to the applied source will be from N to P. And in the depletion region already an electric field exists from N to P. If you keep on increasing the strength of external applied field at a particular strength of external field, the covalent bonds present in the depletion region break down. And because of that, huge number of electron hole pairs are created. And because of that, current starts to flow even under the reverse bias condition. So, when reverse bias is increased, the electric field at the junction also increases. At some stage, the electric field becomes so high that it breaks the covalent bond creating electron hole pair. Thus, a large number of carriers are generated. This causes a large current to flow, and this mechanism of breakdown is called Zener breakdown. Do remember, to observe Zener breakdown, the PN junction should be highly doped. If you have got highly doped PN junction, then the thickness of the depletion region will be less, and the electric field in the depletion region, which is nothing but the barrier potential divided by the thickness of the depletion region, will be high. So when do you observe Zener breakdown? When the PN junction diode is highly doped. Now we need to talk about another type of breakdown. And students do get confused very much between Zener breakdown and the second type, that is avalanche breakdown. First of all, you need to understand what is the meaning of avalanche. If there is a mountain, okay, and at the top of the mountain there is some snow. If this snow starts to slide down, as it moves down, it gathers more and more mass with it from the surface of mountain, and as it moves down, its size keeps on getting bigger and bigger. So sir, what are you trying to explain using this example in avalanche breakdown? Let's say bachon, you have got this PN junction diode and it is reverse biased. So the external electric field is from N side to P side. Now we know that within the depletion region, there are no majority charge carriers. And on the N side, the majority charge carriers are electron. On the P side, majority charge carriers are holes. Now, to understand avalanche breakdown, I need you to think in terms of minority charge carriers. On the P side, the minority charge carriers are electrons. Due to the external applied electric field, in which direction these electrons will experience a force? So they will experience a force in direction opposite to electric field. Now, as these electrons accelerate due to the applied electric field, they gain kinetic energy. And when these electron reaches the depletion region, they can collide with another electron present there. And then these electrons in the depletion region will also start accelerating due to the applied electric field as well as due to the field in the depletion region. So they will again gain kinetic energy. So they will again knock out more electrons. So think that one electron hit one electron. Now you have got two electrons, one which hit and one which got the energy due to this first electron. Now these two electrons are in the depletion region and they are getting accelerated both due to the field in the depletion region as well as external electric field. Now these two electrons can collide with two more electrons and then you will have four free electrons. Then those four free electrons will collide with four more and you will have total 8 free electrons. So this cascading effect gives rise to another type of breakdown and that is called avalanche breakdown. It will help you much more to understand if you have taken the example of the real world avalanche. So at higher reverse potential, due to high electric field, the minority charge carriers while crossing the junction acquire very high velocity. These by collision breaks down the covalent bond, generating more carriers, and then these carriers get accelerated and they collide and they generate even more carriers, and then they collide and they create even more carriers. And in this way you have got huge number of charge carriers, and this type of breakdown is called avalanche breakdown. So a chain reaction is established giving rise to high current because you will get huge number of charge carriers, and the mechanism is called avalanche breakdown. So once more, remember this important line in breakdown. To observe Zener breakdown, the PN junction should be highly doped so that the depletion region will be thin. Since the depletion region will be thin, the electric field strength in the depletion region will be high. Once you apply an external electric field in the same direction, in the depletion region, the electric field might become so big that the covalent bonds there will break, giving rise to huge number of charge carriers. That's called Zener breakdown. So that's all in this hour. See you guys in the next hour where we will talk about transistors and logic gates. Bye bye. So that's all for now. See you guys in the next hour.